All right. So my name is Björn Jarfors. I'm a PhD student at Energy Sciences, the Heat Transfer Division at Lund University. And what I've been working on is the wave transmissive boundary condition, and specifically to modify it into a 3D wave transmissive boundary condition, as well as including some partially reflecting definitions. So in this presentation, I will first give you a short introduction on the theory and previous, or the theory and basically what the development will be done. And later I will go through some OpenFOAM implementations from both well-established, but also a previous student to the course. And after that, I will go through the implementation and a test case. And then lastly, conclusions. So in general, a simulation is performed within a domain, and these domains have boundaries. And a very difficult question sometimes is, how do we define the boundaries? So what I generally deal with is acoustics, and in these cases, we usually need to resolve some sort of propagating waves. And let's assume that we have this confined channel with a cross-sectional jump. And we need to understand what is going to happen in this cross-sectional jump, because if we were to just simulate an entire system, like it will just be way too expensive. So we have this zoomed in part here right at the boundary. And we have this incident pressure wave. Some parts of it is going to be transmitted, some are reflected, because we, due to the cross-sectional jump, we will have an acoustic impedance. And you can think of it sort of as a electrical impedance. So there will be sort of, let's say, an inertia for the radiation of sound towards the second cross-section or the outer domain. And this will result in reflected waves. So in these cases where we have this, if we do not properly define the boundary condition, we will instead get, for example, numerical artifacts. And what we are all aiming for is to have, high fidelity simulations, as little numerical dissipation as possible. And this is actually a huge problem in many cases of boundary conditions, because this low numerical dissipation will actually lead to propagation of numerical artifacts or numerical waves, which survive and persist through the domain. And as soon as they interact with another boundary, they will actually transform into a physical wave, which will it will change the results that you actually get. And this is why we need to have well-posed boundary conditions. And to make sure that we have well-posed boundary conditions, we need to have a method which actually can develop these boundary conditions. And the general method that I've seen used in literature to develop these methods is the Navier-Stokes characteristic boundary conditions. And this is often combined with a local one-dimensional inviscid assumption. And through these, you can obtain the Loader relations, which in turn actually give you the mathematical transportation equation for the boundary. So let's say that we have this this domain where we have 5 waves, where the different waves correspond to information propagating in and out of the domain, as well as at different velocities. And these characteristic waves, for example, then L1 corresponds to the velocity lambda1, which is the convective velocity normal to the boundary, in this case where we have the boundary normal in line with the x1 component. minus the sound speed or speed of sound. So at the outlet, we'll see that we have one wave which is actually propagating in as long as we have subsonic cases where C is, or the sound speed is much greater than the convective velocity. So if we start from the reactive compressible Navier-Stokes equations, I'm not going to go through every detail of these equations, so don't worry. But using these equations together with a characteristic analysis, you can modify the hyperbolic terms that lead to us obtaining the Lodi relations in this form here. So these are already trying to explain what type of information we're going to propagate, and that it's going to propagate into or out of the domain. And these equations we can recast to in terms of primitive variables, so that it's more interpretable and easily implemented in a code where we're already transporting, for example, pressure, momentum, or velocity and density. And further, we can also move forward to talk about them in terms of boundary normal gradients. And if we take the pressure equation for the in terms of the primitive variables together with the boundary normal gradients, we can assume, for example, perfectly non-reflecting condition where we set the L1 characteristic wave to 0, which was the inwards propagating information at the outlet. And then we obtain this equation here to the right, where we just have the temporal term. We have the speed of propagation, which is based on lambda 5, and then the spatial gradient of the pressure in the x1 direction. Now, what we need to ask here is this a good boundary condition? Because usually what we have in the inlet is that we have either a mass flow or a velocity inlet. So there's no real pressure information in comparison to, for example, if you run an experiment where you set the pressure as your inlet, basically, or to determine your mass flow. So what we're saying here is that we are not providing any pressure information at the inlet, and we're not providing any pressure information at the outlet. So basically what you'll have is a system where the pressure just drifts. And to counteract that, what they do in the literature is to include L1 as this relaxation coefficient K multiplied by a pressure minus a far field pressure, or a pressure which you set at the distance outside of the domain. And this is mainly to preserve mean pressure in your system. And the literature also uses basically that you should determine K such that your system converges to the mean pressure as fast as possible, or for as few iterations as possible. And we can also look at it and see that it's pretty similar to, just a simple spring or like Hooke's law, that we have a stiffness coefficient and then we have some sort of displacement. So basically what we have is as soon as we have some sort of compression or expansion right at the boundary, it's trying to relax it such that we reach the mean pressure. Now, if we discretize this by, for example, Euler time discretization upwind spatial, then we obtain this equation here, where we have the phase value at the current time step equals the phase value at the previous time step plus this K, which is now the same K as previously mentioned. That's supposed to be sort of like a spring stiffness constant or a relaxation coefficient, multiplied by the time step size, which is multiplied by this far field value, which is set by the user. And then we have this coefficient here, which is just 1 over 1 plus alpha, which is very similar to a CFL number, which is just your convective speed normal to the boundary and multiplied by a change or your time step and the spatial distance. In this case, the spatial distance will be the distance from your cell center to your face. And then we have the same thing here, but with the alpha in the numerator as well, and the cell value at the current time. So if we, I don't think I mentioned it here, but yeah, basically all right, it says here. All right, so K, as I mentioned, is the same K as the previous one, but multiplied by delta T. But in OpenFOAM, we determine K as the wave speed. So in this case, we'll say that it's U1 plus C multiplied delta T divided by L inf. So this L is supposed to represent the distance until the value which you set as your phi infinite, so your far field value. So L infinity and phi infinity are generally the parameters which the user specifies. But since I mentioned that I'm interested in the partially reflecting boundary condition, let's assume that we do not set L1 equal to 0 immediately during the derivation, but we'll still use the assumption that L1 equals this relaxation coefficient multiplied by the pressure difference. And basically what we see here is that we obtain this extra coefficient in front of this outside domain information, corresponding to something that is scaled or varied depending on what you have as your Mach number at the outlet. And this can be seen as sort of like a transmission coefficient or a reflection coefficient, depending on if you're looking at pressure or velocity. And if we were to similarly discretize this equation, the only difference that we see is that we have this coefficient in front of every single place where the relaxation coefficient appears. So it's sort of there to modulate more implicitly the incoming waves based on your inner domain. So now I'm going to go over more to the OpenFOAM boundary conditions and explain a bit how they are built. So in general, we have a fixed value or a fixed gradient boundary conditions, or we can also have a mix between the two. Furthermore, a boundary condition can either explicitly or implicitly affect the solution. And this is determined whether the boundary condition affects the source term, which is the explicit explicit way of affecting the linear system, or you can have a contribution to the diagonal of the coefficient matrix, which is the implicit way. Furthermore, it can affect these terms in the linear solution of the divergence equation, or the divergence term, or the Laplacian term. Now, I've already mentioned that it's the wave transmissive boundary condition I'm mostly interested in here. And this is a mixed boundary condition, which is based on the advective boundary condition. So by explaining the wave transmissive boundary condition, we also need to explain the advective boundary condition. And the advective boundary condition utilizes the mixed class, which is a general purpose boundary condition, which requires input for the value fraction, the reference value, and the reference gradient. And there we can already see that, okay, the role of the boundary condition, the advective one, is to provide the value fraction reference value, and reference gradient. But before we go into those inputs, the implicit and explicit contributions to the divergence and Laplacian terms that I mentioned are specifically returned to the linear system through the member functions value internal coefficient, value boundary coefficient, gradient internal coefficient, and gradient boundary coefficient. And here I just provided an example of the value boundary coefficient member function in mixed, which simply returns this value fraction multiplied by the reference value plus 1 minus the value fraction times a reference gradient divided by this patch delta coef. And this can be translated to just multiplied by the distance from your cell center to your face. Other functions in the mixed class include evaluate and S in grad. There you also have some mapping functions there, but I will not go through them. But evaluate is an extremely important member function in this class because it checks if the coefficients are updated or not. And if they're not updated, it will call upon the member function update coefficient or coefs member function, which is in the associated class, such as the advective class, to actually update the coefficients. And if they are updated, it will calculate this equation here. Now, this equation is actually exactly the equation which we derived here when we discretize. If we set that the reference gradient is equal to 0. And this is actually the case in the wave transmissive boundary condition, that the reference gradient is 0. And I've been trying to understand exactly why we still have the reference gradient in the boundary condition, and all I can think about is that it's just to conform with the structure of the mixed general purpose boundary condition. And as mentioned, the evaluate calls on the update coefs. So if we have a look at the update coefs member function here, we can see that this will also check if it's updated, and if it's not, it will first check or it will first define the mesh by obtaining it from the internal field. Later, it will check what type of discretization scheme you have for the temporal term. And then it will also store the value of your time step. And if we continue down, we see that it will later take the most important field, which is where you will store, or where all of the, for example, velocity information is stored, and save that. And after that, it will calculate the wave speed. And the wave speed is then determined depending on what is the maximum if the advection speed is greater than 0. And in general, this is the case for, simply. But alpha is then determined as the wave speed multiplied by this delta t, and then divided by the distance from the cell center to the face. This you can see here. This is wrong. This should not be here. It should only be the velocity normal to the boundary. And later we'll check first if we've set an L-inf, which basically checks if we're using the boundary condition or not, in a sense. And if we are, then it will define this K, which we talked about earlier, which is in this case, since it's the advective one, it's the normal, the velocity normal to the boundary multiplied by the time step divided by the preset distance to the far field. After that, it will check what time scheme you're using. And for brevity, we just look at Euler DDT or Crank-Nicholson. And then it will update the coefficient ref value based on the old time plus the field inf, which is set multiplied by the parameter k, and then divided by 1 plus k. And here we can see that the value fraction is updated as 1 plus k divided by 1 plus alpha k. So if we multiply the ref value with the value fraction, we can see that 1 plus k will disappear. And if we go back here, we can see that if we take the value fraction and the reference value multiplied by each other, we will obtain exactly this first term here. And the later term you can derive from this 1 minus f multiplied by the patch internal fields contribution, which is where they get the center value from. Okay, so here in advection speed, basically what they do here is they obtain the 5 surface scalar field, so the phase flux, and then they, I've omitted some of the code here, but they look up what type of patch field you're looking at. So if it's the velocity or the temperature or etc. And then they check the dimensions of the phi, for example, if it's based on mass flow or velocity. And for velocity, then it will return the phase flux divided by the patch magnitude surface normal gradient, which basically says that it will return the normal velocity. And if we move over to wave transmissive case, because this is the main difference between wave transmissive and advective boundary condition, is that it instead returns the phase flux divided by the surface gradient, the magnitude of the surface normal gradient, and the plus the square root of gamma divided by the compressibility of the field, or the compressibility field, which you can also see that it collects from this statement here, or from this definition here. So now we instead have a wave speed that is not equal to the normal velocity, but equal to the normal velocity plus the speed of sound. So to summarize here, we obtain the value fraction, ref value, and ref grad from advective and wave transmissive class through these set of equations. And the evaluate member function in the mixed class determines if these are up to date, and if they are, it returns the current time phase value. And the other ones will, like the value internal coefs, the value boundary coefs, etc., they will return the corresponding value to the linear system which is solved. So I mentioned previously that there was a previous student that tackled this problem before, and what he created was his name is Leandro Lucchese, and he created a 2D wave transmissive boundary condition called Lodi 2D. And as the other conditions, they needed also this general purpose class. So he also created the mixed V2D class. And the initial differences in these include that he merges the advective and wave transmitted classes into low D2D. And then he also specifies that this boundary condition is only meant to be used for a velocity vector. This means that we're removing the templated property of the previous classes. And lastly, he specifies that there are two alphas now, since we will have convective velocities of both u and u plus c. And then we also have that since we're convecting several velocities, we also need to convect them at different ways or in different ways. And the loader relations show that we have a characteristic wave which propagates at, for example, u minus c, u plus c, also just simply convecting by u or u1 in this case. Since it's 2D, there's only one of these L3 and L4 that is included. And in his code, you can see it here, where he includes two advection speeds. One is based on the wave transmitted part, one is based on the advective part. And later here as well, the alpha is based on the advective part, and then here the wave transmitted part. And a part of his constructor in the mix V2D class includes the normal velocity, tangential or transverse velocity, the normal vector, and then here we have instead two different reference values corresponding to the different velocity components. Nothing changed with the reference gradient, but here we also have two value fractions corresponding to the different velocities. And lastly, here we also have the vectors, which I will discuss a bit in the next slide. So these vectors are populated through a for all loop where basically what it's meant to take care of is in case our boundary normal is no longer in line with the x direction. And to simplify the implementation of a 3D, since this is basically a rotation matrix, and in 2D rotation matrix is just in around one axis, but in 3D it would be around 3 axes. So I simplified this and removed it when I performed this, but basically this is the implementation of the rotation matrix where he projects the velocity components to the normal vector, which is determined by the vectors which were populated. Let's see. So this is the modified version where I've removed a lot of these, for example, velocity in the normal direction, velocity in the transverse direction, since they're no longer needed to be stored, since we can gather this information directly from the patch internal field and the old times for the field. But we still have two reference values and two value fractions. Yes, and this is what I mentioned earlier, that you will get from the patch internal field, the velocity vector, and from the old time from the field, the old time and the, previous to the previous time step as well. And to validate this, I took the unconfined bluff body case exactly the same as Leandro used this in his report, and I placed a probe right in the wake, which is a common way to analyze wake dynamics by getting a data series or time series of the transverse or y component of the velocity, and then plotting that. And what we can see here is that the two implementations overlapped perfectly. So it's there's no difference for this case, since the boundary has a normal vector which is completely in line with the x direction. So now it's time to go over to the actual implementation part. And since we have an extra component to transport, we need to include an extra value fraction and reference value corresponding to this third component. So this is the initial part which is done. And the results in the change in the evaluate member function in the modified mix v3d to include an extra component in its return function, which is seen here, that we have this last component here. And as I mentioned earlier, it was 3 components now which are calculated. So just to give you an idea of like the comparison of, for example, the value boundary coefs member function I showed you earlier in the mixed and the modified mixed v3d class now, is that we calculate these three you know, value u1, value u2, and value uc, and then we multiply them by the corresponding vector so that we know which direction it's actually corresponding to. And in the mixed one, we also have this part here. So this is 1 minus value fraction multiplied by the reference gradient divided by, or multiplied by the distance from the center and the face. And since I mentioned that reference gradient is always 0, this is removed and not included in this return code, or the code, the member function's return statement. Similarly, an extra component is used in the rest of the member functions regarding velocity computations. So if you remember here, it was where we checked the linf, so if we're actually using the boundary condition or not. And then it updated the k here and so on. And then here it starts to calculate all of these different contributions. So now we have 3 of them instead of 2 each. So to recap here, is that if we wanted to go over to a partially reflecting boundary condition instead of this perfectly non-reflecting, then we needed this extra coefficient. And this coefficient was, like I mentioned, you know, it can be seen as transmission coefficient, and then for the velocity can be seen as a velocity coefficient, and the sign is changed. So now we needed to implement this instead of this equation, which is rather simple because we actually only need to implement this coefficient in front of the k. So to implement this coefficient in front of the k, we needed also to obtain u1 minus c in the code. So basically what is done here is simply to duplicate the advection speed for the wave transmissive part and take the negative of the or subtractive speed of sound instead. And then we define the WUC2 as the minimum of the advection speed and the scalar 0. Because here we're expecting that for subsonic cases, which is what this boundary condition is applied for, that C is greater than U, so then it should be a negative value. So then we need to get the minimum of it. Otherwise, we would just have a 0 all the time. And then we define this partially reflecting coefficient, which is simply this R here. Now, this is just a clarification, which I mentioned. This is later implemented in the value fraction and the reference value definition. So if we go to the reference value definition, we can see that this is simply multiplied by decay in both the numerator or denominator and the numerator. So now over to the compiling. For some reason, this structure did not appear here, but basically what the codes that we have here is the modified mixed V2D, V3D, and the modified low D2D, 3D, and 3D partially reflecting. And the structure is kept the same as OpenFOAM standards, and this is the same as Leandro used as well, where we divide the boundary conditions into basic and derived folders. And we place this in the user directory source finite volume directory. And for the files, for the compiling, you simply include all of the different codes which are to be compiled. And in this case, nothing has changed from Leandro's case, since we are using the same mathematics and operations, so that we only include the following codes. So over to the case description. It consists of an unconfined bluff body, as previously introduced. It's the same case as Leandro ran here, where we have 120 meters per second in the x velocity as initial condition in the inlet boundary, with 0 gradient for temperature and pressure. Since it's unconfined, we're using a free stream velocity and free stream pressure at the top and bottom, but a 0 gradient for the temperature. And the velocity is case specific, so this is where we implement our different boundary conditions. The temperature is an advective boundary condition, and the pressure is wave transmissive. This dashed box here is where the case results will be presented for, so that you can actually see what's happening. So the different cases here include just wave transmissive with an LINF set to 10 meters. And later we'll try the low D2D, and this is the Leandro's low D2D. So not the modified one, even though they're identical in results. And then the low D3D and low D3D partially reflecting. In this case, we use the row pimple foam and the max current number of 0.3 to have it 3D. I chose 10 cells spanwise direction, since that resulted in perfectly uniform cells right behind the bluff body, and this corresponds to a simulation of 200 cells, 200,000 cells, and the Reynolds number, if you base the Reynolds number based on the bluff body size, you get it to approximately 40,000. So it's a pretty turbulent case. And if we look at, so all of the results I will be presenting in the first part here is the mean values to the left and the prime to mean values to the right. And the prime to mean values is just the mean fluctuations, which is squared. And what we can see here is that the pressure field is actually very similar to for all of the cases. And case A is actually not case 1 here. So this might be a bit confusing for some. But case A is the low D2D, case B is the low D3D, case C is the wave transmissive, and case D is the partially reflecting boundary condition. So what we see here is that the RMS squared is actually only slightly different, mainly for between the Lodi 3D and the rest of the cases, where you can see that there's a slight larger magnitude right on the top side of the vortex shedding here. So this sort of indicates that there are less reflections because there's less coupling between the pressure field and the vorticity dynamics. Going over to the x velocity, again, the mean results of the x velocity looks very similar. The pressure or the velocity fluctuations in the x direction look very similar to each other. There's a slight weakness in the upper fluctuations of the vortex shedding, except for the Lodi 3D where it's very symmetric. And this is again most likely due to the lesser amount of reflections. And go over to the y velocity. In this case, it's very difficult to see any difference in this. It just looks like this is treated exactly identically in the mean or the statistical fields. But if we go to the z velocity, so this reflections here are expected since we do not actually transport the z velocity in the Lodi 2D case, only transport the x and y. But here we can see that these reflections couple with the vortex dynamics and actually result in higher reflections here. Furthermore, the Lodi 3D is actually very similar to the wave transmissive. You can slightly see some difference. It's difficult to really assess through these mean fields here. But if we have the partially reflecting case, our modulation corresponding to reflection term results in larger velocity magnitudes, mean velocity magnitudes in the z direction. Furthermore, the velocity z direction fluctuations show quite a substantial amount of fluctuations in the partially reflecting case in compared to the other cases. But again, here the wave transmissive case and the Lodi 3D case look very similar actually. So now it's no longer the mean values here for the these are only the mean fluctuation values in the x z and y z components, and again we see these reflections for both of them, which is again expected. Larger fluctuations for the partially reflecting in this case as well, and only a slight difference between the Lodi 3D and wave transmissive case. So a common way to analyze, as I mentioned, was taking the y velocity behind the bluff body and tracking it over time. And after that, you can do a frequency analysis. And we commonly refer this to the straw hull frequency. And in a very clear vortex shedding case, you would have a very clear peak for the vortex shedding, which corresponds to the Lodi 3D case here, which has the clearest peak. And then Lodi 2D actually has the second clearest peak here, but then it also has twin peaks right next to it. And for me, it's very expected that you see a broader peak for the partially reflecting frequency peak for the shedding, because you intentionally have more reflections which couple to the vortex dynamics, and that will sort of perturb the vortex shedding. Since it's a hydrodynamic instability, it can be very sensitive to pressure fluctuations. Yeah, and you can also see that the wave transmissive one corresponds to a double peak here It's sort of hidden behind the blue one here, but it's a much lesser peak than the Lodi 3D, indicating that there's some intermittency, which I will address later. So this part might be a bit difficult for some to understand that don't deal with a lot of like nonlinear dynamic analysis. But this method of analysis is based on a Hankel matrix. So it's still the same time series, the velocity, the y velocity time series, where you actually take that series and you introduce like a time delay. So in your Hankel matrix, you will have the original time series in the first column, and then you have a time delayed time series in the second column, and then you can repeat this based on your time delay. So one of your time delays, 2 times your time delay, etc., based on how many dimensions you need. And the benefit of this is that you can have this 1D signal and you can inflate it such that you can find out hidden dynamics in your system. So this is what I did here, and I had a time delay of 10 time steps and a dimensions of 100. So basically what happens if you overinflate it is that the phase space reconstruction becomes very difficult to interpret because you're basically folding it in on itself. But this method also follows diffeomorphism, which is basically that you will conserve the topology of the structure, but not the geometry. But basically what we see here is that the boundary condition actually affects the initial condition of the trajectories. So here is the initial condition sort of following a hook, and then you see that they all sort of tumble, looking almost like a bunch of rubber bands that got tied together. But if we look from the top view instead of the ISO view, we can see that there's this sort of elliptical structure, which is generally what we like to see in these cases, because this means that we have a limit cycle behavior. And this is usually connected to a strong sinusoidal signal, which indicates that we have a very strong vortex shedding, for example. But all of the parts here in the middle, so this is actually taken from a part of the signal where it's sort of statistically converged, let's say. But all of these parts in the middle are basically the intermittent changes of the vortex shedding dynamics. And it's a bit difficult to see here right immediately, but you'll have to trust me when I say that wave transmissive includes more intermittent behavior than the other cases, which could be some sort of diffuse, some sort of consequence of not actually treating all of the components of velocity in the right manner, so that we get some sort of weird reflections, which may be of low magnitude, but it depends. But yeah, to summarize and conclude, what has been done is to create a well-posed boundary condition where we use the traditional Navier-Stokes characteristic boundary condition method to obtain Lodi relations. We identified the mixed as a general purpose boundary condition class, which requires input for the value fraction, reference value, and the reference gradient, which are obtained through the update coefs member function in the advective class. The wave transmissive class alters the definition of the member function advection speed in the advection class or advective class. The evaluate member function is in mixed calls the update coefs member function in the advective class to obtain these coefficients in order to calculate the face value at the current time step. And a simplified version of the Lodi 2D and Mix V2D was created in order to make the transition to 3D simpler. And this included neglecting the rotation transformation. A 3D non-reflective boundary condition was developed to correspond, which corresponds to the modified Mix 3D and modified Lodi 3D codes. And then it was further elaborated with a partially reflective formulation. And with that, I would like to thank you for listening. And I'll leave you with this quote from Dean Kamen, the inventor of Segway. Thank you.